some pictures. It's kind of hard to see a 3D shape on a 2D surface, but I'll try to show you. And then sometimes we can get volume by rotating around the x-axis, y-axis, or some other line. So it's sort of like going out towards you and then behind, and out towards you and sort of behind. Actually, those are the more fun ones. Okay, so we're going to start by building a 3D shape from my graph. So volume, we have to remember volume is area times height. Does that make sense? Like length times width times height for a cube, something like that for a box. So we basically got the area of a 2D shape, area of that, times a third dimension. Width or depth or height or whatever you want to call it. Does that make sense? This is how I get 3D. There's an area and then I have to do a third dimension. Okay. Yeah, we're going to start with kind of simple shapes and then build on that. The base can be any shape, and then we're going to build up from the base and make cross sections. That's going to be the key. We're going to make cross sections using some shape. Squares, rectangles, triangles, circles, that's what's going to be coming out at. Semicircles, something like that. Okay, so let's break this down very simplistically, hopefully. We can estimate the volume. We'll shade it by S by cutting it into a lot of pieces, similar to when we did area and when we did integrals, with each cross-sectional piece actually being whatever I'm saying is coming out at you. A square, a rectangle, triangle, semicircle, circle, whatever. Within that region S that's on the paper, on the graph. And then we can estimate the volume of S by adding the volumes of all these smaller individual cross-sectional pieces, and we'll get the exact volume. Because as I approach, as the number of these cross-sections approaches infinity, I should get the actual volume. But we're not going to really have to do that in pieces. What if I have 4 squares? What if I have 6 squares? Hey, I need more squares. Okay. We'll just skip all that and go right to the chase. So this is how we're going to do it. We're going to have our base really on the graph, S, in a plane on the graph, and then we're going to make a cross section, and we're going to do a bunch of cross sections, slice S into n number of cross sections, n number of slabs, all with equal width. Change of X is always going to be the same. So that each slice will be with that particular shape, a semicircle, a square, a rectangle, whatever we say it is. But the widths are always going to be the same. And then we're going to add up all the slices. So look at this. It should be then that the volume equals the area times the width. There's my 3 dimensions right there. And if I just add up all of those cross sections, I mean, what if they were a bunch of squares? Well, add up all these square pieces. Here's the volume. I mean, they got a little bit of depth. So length times width times, or length times height times width. Length times height times width. Length times height times width. I'll just keep adding it. The thing is, I don't have the same size. I got the same depth of all these pieces coming out at me. But if we're saying, hey, they're semicircles, they're not all the same size of semicircle. If my graph is really wide here, I got some big semicircles coming out at me. If the graph is not very wide. I got a little tiny semicircle. But here's, I mean, would you agree that's good? 3 dimensions here? And that's gonna stay consistent. And like if we're talking squares, length times height, length times height, length times height, that formula will stay the same, but the length and the height may be different, but the width is always gonna be the same. And I know from playing with this sort of process before that as n approaches infinity, can I just change it to that? So guys, guess what? In order to find the volume, take the integral of the area. If we add up an infinite number of whatever shapes I've got, 3-dimensional shapes, I can just take the integral of 3 dimensions. dx, the length, that becomes dx, and then I got the area for me. That's what I'm gonna do. So specifically, until I show you the pictures, A times x is the area of a moving cross section slicing through this 3D shape. We're gonna start perpendicular to the x-axis, so I'm gonna be moving along the x-axis, as I often was, except on this warm-up, we kind of moved across the y-axis. But we will change that, so make sure to integrate with respect to the correct variable. Sometimes I'll be moving along the y-axis, in which I wanna do dy. And sometimes I'll be moving across the x-axis, and so I wanna do dx, which is what we'll start with. Okay, it's sometimes a little easier to figure out which axis when we're doing volume, because they pretty much tell you. Okay, so I did assign an AP video after we do some. So here's the shapes we're gonna be making. So I've got this graph, and you might say, oh, I want the cross sections to be rectangles, and the rectangles are gonna be coming out at me. Well, these are gonna be bigger rectangles over here than these are gonna be over here. You might say, hey, here's this parabola, and I've got these squares coming out of that parabola. Well, when the parabola is really wide, I got some pretty big squares. And when the parabola is not so wide, I got some little tiny squares. So it's not all the same exact, I mean, it's the same shape, but they're not the same size. Here's some more 3D effects. Hey, look at this one. This one's coming out at me as triangles. Can you kind of see that? It looks like this one's coming out at me, looks like I got an exponential function, coming out at me as semicircles. And this one looks like rectangles, this one looks like triangles. This one's either squares or rectangles. Notice as the base gets wider, your shape is getting bigger. And then when it's not so wide, it's not that much coming out. I'm trying to show what these look like, because it's gonna be kind of hard to somewhat visualize on the 2D. Here's a whole bunch more. I don't know if these do the justice that the other ones did. But anyway, hey, let's just do a couple, okay? We'll play with it. So, oh, what I gave you, by the way, the examples we're gonna be doing in class, also the notes about when we rotate. So that's at the end of the examples. And then the very last sheet are some teacher-generated, if you wanna do some extra credit. So you can rip the last page off and do extra credit. So that's why it seems kind of thick, because I've got the notes in there, and then I've got extra credit at the end. Okay. So let's try this very first. Let's find the volume of the shape with the base bounded by the circle. X squared plus y squared equals 4. And the cross sections are gonna be squares. So let's think of the base as having, or the entire 3D shape as having its base on the paper, on the graph, but rising out from it or coming towards us off the paper. So as best we can, we're gonna try to draw a picture of what the heck is going on. So, and I will tell you, I am not artistically inclined. Anyway, so I do know this. That's a circle with the center at the origin and a radius squared is 4, so 2. Let's see if I can get this kind of sorted. There's my kind of sort of base circle. And the cross sections coming out of it are gonna be squares. And we'll just say we're going across the x-axis. So I'll draw one square. Sorry guys, but it is kind of coming out at me. That square is coming off the board, coming towards you like this. That's what's going on right there. And this square actually is not a 2-dimensional square, it's a 3-dimensional square. So it has some width. We're gonna get to a point where we're not even gonna draw that. So it really has some width to it. First of all, do we sort of see what we're doing here? We got some little squares over here coming down at us. These squares are gonna be real tiny. Those squares aren't so big.
What's the point of having a circle base? Like, it's just there.
The point of having a circular base. Yeah, so you can do those 3D shapes I wish. You can do a box. Those are boring shapes. You can build a thermos. There's a circular base, that thermos.
I know, but like the cross sections are squares.
Oh, you want some sort of cool shape. That shape is gonna come up here and have this biggest square right here and then come down here and have the smallest squares. It's gonna be a cool shape. So the biggest square on here is gonna be right here. And then they get smaller as you get. Got real small squares. Okay. I know the volume of this square right here is width times side squared. Because that's the area of the square, right? Because that square's got some depth to it. So what I would like to do, we'll eventually skip this. I wanna add up all of these squares in here, which are going to have side squared. Can I just call that S squared? Times the width, the thickness of it. Change of X. That's gonna be consistent for each square. So the area of the square times the thickness of the square. And I'm gonna go from n equals 1 to infinity. Well, I know that just becomes this. The volume will equal the integral from a to b of s squared, and that will become dx. Okay, so let's stop. Does that make sense that that's the area of a square? Side times side? And then because each of these have, because we're doing volume, each of these have a little bit of thickness. With, we're gonna be consistent on thickness of dx. So basically it's just the area. And let's put in actual values for this formula. The volume will be, if I'm going in terms of x, aren't I moving from -2 to +2? From -2 to +2? Because it's a radius of 2. What is the side here? Man, here's another square.
Does the circle limit the square?
Yep.
So it does have an effect on the side.
Yep. Yeah, because this side is really big here, and this side is not as big right there. And it's coming out as much as this side. This side is the same as that side. I don't know. To me, it looks like it's going all the way up to whatever y is. It's going all the way up to whatever y is.
Oh yeah. Would it be too wide because on the because it's two of those lines.
Yeah. So I would say that's y, and that's also the same distance.
Yeah.
So I would say, hey, each side is 2y. And then I want to square it. Which I would say is the integral from -2 to 2 of 4y squared. Oh, dx. Guess what I'm gonna have to do?
Do we know?
I wanna put some x's in here, not y's. Otherwise, y is not changing. Oh, well, all I need to do is write this equation. X squared plus y squared equals 4. Why don't I just subtract the the x squared? So y squared is 4 minus x squared. Now why don't I just put that in here? Integral from -2 to 2 of 4 onto y squared is 4 minus x squared dx. Now it's in terms of x. And this you could probably put in a calculator. Yeah, if you want to clean it up a little bit. Integral from -2 to 2 of 16. Actually, probably pull this is what I would do. Where's my list? Oh. you don't have to, you can put this in the calculator. 4 minus x squared dx. That's not a hard integral. Take it from -2 to 2. Do you want me to take the integral for you or just tell you what the answer is? I can't even read my writing. Well, that's gonna be what? 4 onto 4x minus x cubed over 3. And I wanna take that from -2 to 2. I mean, we can plug in the 2, right? And then minus plugging in the -2, which would be adding, obviously. And this is what I get. 42.667. We don't know what it's being measured in, so we'll just say units cubic. Just take the integral of the area. Figure out what the cross-sectional pieces are. But they are gonna change. They're not gonna change their shape, they're gonna change their size. Because those cross-sectional pieces are based in this shape. And in some places, this shape is gonna be really wide, so the piece is gonna be big. And in some places, it's not gonna be quite that wide, and that same shape is gonna be smaller. But it's going up to whatever the graph is. Or the graph's gonna tell me how big the shape is.
What does this look like?
What does it look like?
Yeah.
It might look like,
But like,
that was way back here. Well, there's what it would look like if it were triangles. Maybe picture these as little squares. So you got little squares where it's close together, and then it builds up to a big square, and then well, there's squares. You could say this is squares coming out of that shape, even though it's not a circle.
yeah, I see.
Let's go. Let's do it now. Where's number 2? Oh, okay. We'll stick with the squares. How's that? We'll stick with squares for now. We can do any shape we want. But squares is a good one to start with because the coming out at you, all the sides are the same. Why is this so hard to read? Okay, what's going on in this one? Find the volume of an object whose base is bounded by the x-axis in that parabola, y equals 4 minus x squared. And my cross sections are gonna be squares perpendicular to the x-axis. That's perfect. I'm moving along the x-axis. So I kinda want a rough sketch of it. Doesn't have to be a perfect sketch. 4 minus x squared, or minus x squared plus 4. Well, that's gonna look like this. And then it's gonna hit -2 and 2. So here's the upside down parabola. And with the x-axis. So it's gonna be coming out of that shape. And I'm I'm building squares again, so I'm just gonna, hey, the squares are coming out of this shape. So the volume. Hey, can we just skip that I'm adding up an infinite number of squares? Different size squares, but they're all squares. And we'll just skip right to the, hey, I need to take the integral. Let's see, I'm moving across the x-axis. Hey, that tells me it's gotta be dx right there. That tells me that. And if I'm moving across the x-axis, I'm not going from 0 to 4, that's moving across the y-axis. I'm going from -2 to 2. -2 to 2, and I'm moving across the x-axis. So that locks me in. Now I need to figure out the area of that cross-sectional shape. Hey, what's it going up to? It's going up to the curve, isn't it? It's going up to the curve, which is y, and a square is y times y. Y times y is a square, right? But I'm doing it in terms of x. So I need the integral from -2 to 2. It's already in terms of x. Y is 4 minus x squared. 4 minus x squared. Squared. Looks like dy, dx, in terms of x. So each side is going up to this curve, and that curve is 4 minus x squared. 4 minus x squared will be bigger here than it is here. And I'm going to add all of those together. Well, that's just going to be, if we're going to do it by hand, integral from -2 to 2. What is that? 16 minus 8x squared plus x to the 4 dx. And I think that integral is going to be what, 16x minus 8x to the cubed over 3, x cubed over 3, and that's going to be x to the 5th over 5. And I want to take that from -2 to 2. Now, could we plug all that in? Do I need to plug all that in? Plug the 2 in minus plugging the -2 in? Are we okay with that? Can I just give you the answer? I'm gonna give it to you in fraction. Because I did it by hand. That's gonna be 512 over 15 units cubed. Hopefully we're okay just plugging in the integral, right? Big top number plugged in minus plugging in the bottom number, right? That's what I got. Volume is the integral of the area. I'm gonna do one more. Can we do one more? Since 3 of you I won't be seeing. Where's my staple? Let's do one more. oh, we get to use a calculator. Find the volume of an object whose base is bounded by the x-axis. X equals E, and the curve y equals ln x. And this time I've got rectangular cross sections. Well, let's get to that one in a minute. Let's kind of draw what's going on here. The x-axis, draw the axis. The x-axis, x equals E, well, that's somewhere over here. What, E is like 2.718 something. We'll just call it E. And the curve, natural log of x. Well, natural log of x, it's gonna cross here and do that. And so the base is bounded by the x-axis, x equals E, and that natural log of x. And then it continues down here. There it is. Of course, my rectangles are going to be very small here, but my rectangles are going to be kind of big over there. And these are rectangles. Well, specifically, how are these rectangles being built? The rectangular cross sections are 4 times as tall as the given base. Well, we know what the base is, right there. And then it's 4 times as tall. That's what's coming out at me. So I got some really, here, they're really gonna come out far. Here, not so far. I need to figure out the area of a rectangle.
Side by side.
Base times height, right? Isn't the base that? And that's what's changing. So can we just skip all the, I need to add up an infinite number of rectangles and just skip to the chase. And it looks like I'm going perpendicular to the x-axis. So I'm going across the x-axis. So it looks like I'm going from 1 to E. Volume equals. Going from 1 to E. The base times height, you said the, so base is this thing, right, ln x? And the language told me the height was 4 times the base. Yeah, 4 times as tall as the base. So I think I've got the height is 4 ln x. Are we okay with that? The base is ln going to the curve, and the height is 4 times whatever that was. So I can clean that up a little bit. Integral from 1 to E of 4 ln x squared. Using a calculator. Well, why can't I just use the calculator now? I mean, you could pull the 4 out and just do integral from 1 to E ln x squared and then multiply by 4. Either way, but can't we just, if we're okay with how it was set up, why don't we just put it in the calculator and what do we get? 2 point, what?
87.
Oh, that's more like 3 decimals. Here we go. Okay, this is how we're gonna do the shapes coming out at me. Okay. When I see most of you again, we'll be doing triangles or semicircles or maybe back to square.